working here. Now we have two speakers. The first speaker is Claudia Moreno. She has finished her PhD recently, some weeks ago, under the supervision of Eduardo Serpa from Valparaíso, Universidad Técnica Federico Santa María, and Emmanuel Crepeau from Université Grenoble. She's now at Université Paris-Saclay. So, please, Claudia Moreno. Okay. You can start now.
Okay. Good afternoon. Thank you everybody for being here. Thank you to the organizer for the invitation. And today I will talk about the control on impartial different equation system of dispersive time. And this work is joined with Emmanuel Crepeau and Eduardo Serpa. Okay, in the outline, initially I introduce my thought, and second, I will present I present the motivation of this work. After that, we study the controllability of the Cortez-de-Vries equation and an star-shaped network, where we consider the previous work, and we introduce the control problem, and finally, I present how we obtain the exact controllability of the system. Okay, in the control community, we are interested in obtaining control properties for different equations. For example, there are control results for the KDV equation, and in this work, we consider a system with n KDV equation, and in general, we study the particular case when we have, in general, we study the case when we have, when the number of the control is less than the number of the equation. Now, I don't know what happened with that. Okay, I have a little problem with the slide. Okay, don't worry. Okay, now we're looking for an answer for the following two questions. The first one, can you control a system if you have n couple KDV equation, and what is the minimum number of the control? Initially, we studied the controllability of the KDV equation and an star-shaped network. Okay, the system. I wanna show you an example when we have three controls. When we have three KDV equation, three control at the endpoint of the network, and with now control properties when we have another control in the center of the network. In the general case, when we have n a natural number, the control problem is given by the following equation. Here we have in blue the nonlinear part of the system. The function f0 is the control in the center of the network, and the function g are the control at the endpoint of the network. We also have a condition alpha larger than n-half. With this condition, okay. With the condition alpha larger n-half, Marin and Crepeau has proved the exact controllability when we have n control at the endpoint of the network plus n control in the center of the network. What is the goal? The goal, we want to prove that the system is controllable without the control in the center. And we also consider the case alpha. We also consider the case alpha equal n half. Now, the control problem is given by the following equation. You can see this is a system without the control in the center. We have the nonlinear part in blue, and we only have the control at the endpoint of the network. And we also consider the condition alpha equal n half. Now, initially, we studied the well-posedness of the system. For that, we define these spaces, and using the semigroup theory, we can obtain an unit solution of the system. We also have estimation of the dissolution given by the theorem 1. Okay. After well-posedness, we study the controllability of the linear system. The linear system is given by the following equation. Here we only have the control at the endpoint of the network, and to prove the subcontrollability of the linear system, we define an operator that take the control function to, okay, to prove the subcontrollability of the linear system, we define an application that sends the control to the solution at time capital T, and by duality between controllability and observability, this is equivalent to is only necessary to prove the surjectivity of this operator. And by functional analysis, this is equivalent to obtain an inequality for the advanced system. It's for that we study the advanced system. The advanced system is given by the following equation, and in the following theorem, we have the subcontrollability is given by the last inequality for the advanced system in the theorem 2. Now, to prove the subcontrollability, this means to prove the last inequality, initially, we multiply the advanced system by a general function, and integrating by part, we get the equation 4. Now, we consider particular function. For example, we take Q equal T, and we have the first inequality. You can see in this inequality, we have the solution of the advanced system at time capital T. After that, we consider another function Q equal 1, and we have another inequality. Finally, we choose a polynomial function, and this function is positive, the derivative is negative, and the second derivative is positive. Using this estimation together with the Poincare inequality, we obtain a last inequality where the constant Tn must be positive. The value of n is given by the last expression. You can see this is a quadratic equation and the variable capital T. Okay, and now we want to study the discriminant of this quadratic equation. We want to study the discriminant, and we find that this discriminant is positive if you have the condition for capital L and capital T. For example, capital L must be small enough and capital T between the root of the quadratic equation, which are given by the last expression. Okay. Now, using this condition for capital L and capital T, we can find positive constants and we have the inequality for the advanced system. We can find a positive constant and we also consider the case alpha equal in half. By simplification, we simplify and we obtain an inequality. We simplify and we obtain the first inequality where we also have the condition for capital L and capital T given by the last equation. Okay. Then by duality, we can obtain the exact controllability of the linear system given by the theorem 3. This means we can find n control driving the solution up time capital T to a final state. Okay, after well-posedness and the subcontrollability of the linear system, we study the controllability of the nonlinear system. The nonlinear system is given by the following equation. We have again, and we have in blue the nonlinear part of the system, and we also have the control at the endpoint of the network. Now, we want to prove the exact controllability in local way of the nonlinear system given by the theorem 4. Okay, I want to present the idea they have to how we obtain the exact controllability of the nonlinear system. Initially, we consider an application that sends a function B to the sum of the solution for the following system. The first one is a linear system without control. The second one have the nonlinear. The second one have the nonlinear part on the other side, and the last one is the linear system with the control. And we know that the last system is controllable. This for that we can find n control G driving the solution of the last system to a particular state. This means we need. This means it's only necessary to find a fixed point of the. This means it's only necessary to find a fixed point of the operator. For that, we use this estimation given by the well-posedness together with the continuity of the nonlinear part, and under condition for the constants, we can apply the fixed point theorem and we obtain the exact controllability of the nonlinear system in local way. Okay. Now, I wanna, now we are working on other control problems. Initially, we studied the boundary subcontrollability of the Hirota-Satsuma system. The Hirota summa system is given by the following equation, and we have here 3 function controls, and okay, the Hirota summa system is given by the following equation, and we have here 3 controls, and we want to prove the exact controllability of the Hirota summa system given by the theorem 1. This means we can find 3 controls. We can find 3 controls driving the solution of the Hirota summa system to one particular state, uptime capital T. Okay, we can obtain the exact controllability of the Hirota summa system. This means we can find 3 controls driving the solution uptime capital T to one final state. And okay. Finally, we have another control problem. This is for unforordered parabolic system, and I really like this problem. The control problem is given by the following equation. Here, okay, the system is coupled. The system is coupled by the blue part, and you can see here we have 2 equations and only an internal control. The first equation is coupled by the derivative and the function, and the second equation is coupled by the derivative. Again, we have here 2 equations and only 1 control. Okay. Just take to finish that. Okay, we continue. What is the goal in this part? For the forordered parabolic system, we want to prove the null controllability of the T system. Okay, this is conjecture. This is a conjecture because it's not proven yet. But initially, we studied the well-posedness of the system. Again, we want to prove the null controllability for the forordered parabolic system. This is a system with 2 equations and only 1 control. And for that, this result is given by the conjecture 1. This is a conjecture because it's not proven yet, but we study the well-posedness of the system. And for the well-posedness, we consider initially the main part of the linear operator given by the first equation, and we use the semigroup theory to obtain a unit solution of the first system, and to include the no constants parameter, we use a fixed point argument. And we obtain the well-posedness of the system. After well-posedness, we study the fourth-order parabolic. After well-posedness, we consider the system with two controls. And now we prove that this system with two controls is controllable to zero. The null controllability is given by the following theorem. And to prove the null controllability of the system with two controls, we use Kellerman estimation. But that normally when we want to prove the null controllability, and this part to prove the null controllability, this is equivalent to obtain an inequality called observability inequality for the advanced system. The observability inequality is given by the following equation, and the advanced system is given by the last equation. Okay, what is the map? Initially, we consider, we study the well-posedness of the system. After that, we study the null controllability of the system with two controls. We prove the null controllability of the system with two controls. And to prove the null controllability, we need to prove an observability inequality. And for that, we use the Kellerman estimate to obtain the null controllability of the system with two controls. Okay. Okay, to obtain, okay, after the null controllability of the system with two controls, we need to remove one control. We remember, we have two equations and only one control. To remove one control, we use the algebraic solvability method. What is the algebraic solvability method? Okay, this initially in this method, we define an algebraic problem. After that, we need to find a differential operator, and we can find also the adjoint operator. And using this differential operator, we can obtain a solution of this algebraic problem. And finally, this is possible if the control that we use in the algebraic solvability is regular enough. Then we can obtain the null controllability of the we can obtain the null controllability with only one control. Okay, again, we ask for the last. Okay, again, for the last parabolic system, we prove the well-posedness. We prove the null controllability with two controls. And to remove and control, we use the algebraic solvability method. And in this method, we need an control regular enough. And for that, now we are working to obtain to prove the regularity of the control. We need to obtain a Kellerman estimate with no homogeneous condition. That implies the conjecture one, that is they. This means we can obtain the null controllability with only one control if the control that we use in the algebraic solvability is regular enough. Okay, we are here some reference. And thank you for your attention.
thank you, Claudia. Maybe you have time for one or two short questions. If someone in the public wants to make some question, can raise their hand or. Okay, well, I have a question. So for your first problem, Claudia, KDB.
Yeah.
Do you have?
Tengo un problema con el pulsor porque cuando se parte, pero en la primera parte.
Yeah, KDB, KDB. Do you have any idea about the answer of the question of the minimal number of controls? Because what's your first, no? Because you were able to remove one control. That's no?
Yeah. Yeah.
Okay, but you have any idea if it is possible to have still less controls?
Okay, this is a so important question because we are talking about with Eduardo, and es que también okay, it's depend of the.
So it's an open question, no?
Yeah, this is an open question, but because depend of the what control you want to remove, you know.
Okay. Okay, well, I guess it's not so easy to, yeah.
Yeah.
There is someone in the public, Karine, maybe she wants to make a question. Please go ahead. You can unmute your microphone. Okay. Now you can unmute.
Okay, I could open the microphone. Thank you. My question is about the controllability of the linearized KDV equation.
Oui.
You use the multiplayer method, and you do not use the usual proof by contradiction.
Okay.
I would like to know which step of this usual proof does not work.
Yeah, it's so nice. It's so nice question. The answer for that is that I want to find that. I don't know why I don't know. Okay. Normally, when we want to prove the subcontrollability for the KDV equation, not in the, for example, in the article of Rossier, the way to prove the subcontrollability is for contradiction, you know, contradiction.
Yes.
But in this part, it's not possible because we have the condition for alpha. This means we use the directly way because for contradiction it's possible that's the point. It's possible, but we use another method. It's only for that.
Okay.
Okay. So in the article of Emmanuel Crepo, il a montré, il proved that il proved the subcontrollability using and by contradiction, and we only want to prove in the other way. This is the reason, really, is because this work with the multiplication, and it's for that. But you can do it. You can do it with the contradiction.
Okay. Okay. And I have a second question. It is about the boundary condition at 0 that you choose. Okay. I would like to know why you choose this boundary condition at 0, and if there are other choices of boundary condition at 0 for which we would have well-posedness.
Excusez-moi, j'ai pas compris.
So I would like to know why you choose this boundary condition at x equals 0.
Ici, cela?
Yes, yes.
Okay, the first condition is the continuous condition.
Yes.
Because these are some.
The second one.
And the second one is for the energy, because in the first article, that is made the article of Manuel Crepo, this is an article for stabilization, and you need to study the energy. This is for the energy.
So it is a natural boundary condition. There are no other choice.
Excusez-moi, j'ai pas compris.
So it is a natural boundary condition.
Natural.
There are no other choice.
We can choose another condition. Okay, normally in this problem, we want to improve the previous result, you know? And in the previous result, they consider the condition in the second derivative. And we extend with them, but we continue with this condition for improve the previous results. It's for that.
Okay.
Yeah, it's possible. I think it's possible to consider another condition, I think. But for the problem, for this particular problem, we consider the condition in the second derivative because it's for important the energy. When we study the energy, we need the conservation of the energy. And it's for that this condition is so important.
Okay, thank you.
Okay, thank you. In order to have time for the next speaker, so if you have another question, you can write Claudia. So thank you, Claudia.
Okay.
Thank you very much. We pass right now to the second speaker.
Okay.
You are ready. Okay. Irene. You can share your file. Okay. Okay. So now we have Irene Marin-Gayte from Université de Sevilla. She's finishing her PhD under the supervision of Enrique Fernandez Cara. So Irene, you can start. Thank you.
Okay. Thank you very much. Good afternoon or good morning. First of all, I would like to thank the organizers of the seminar for giving me the opportunity to speak. My name is Irene and I'm PhD student of Seville. And in this talk, I want to present a work with my director, Enrique Fernandez Cara, and the title is Theoretical and Numerical Bi-Objective Optimal Control, Nash Equilibria. And in this work, we approach to the study of Nash equilibria from the point of view of control theory. In particular, we will study the Nash equilibria associated to a semi-linear elliptic equation and a stationary Navier-Stokes equation. This is the outline of the presentation, and we will begin by motivating our study and introducing into the framework of multi-objective optimization. And after we will deal with two problems during this presentation. The first one is a semi-linear type problem for which we will detail the definition, the characterization, and algorithm of Nash equilibria. And this study will help us to illustrate the more complex problem, which is Navier-Stokes, stationary Navier-Stokes equation. And we will end the exposition with leaving several still open questions. So we want to motivate the problem, and one of the great motivation of this work is the application to the serious problem of garbage patch. Now there are 5 plastic islands that are floating in the ocean with the problem that this generates. And there are many groups that are concerned with this problem and study the how to end with this island. One of these solutions is that System 001, Mission Plan 2018, that is here in this image. And the method is, the solution is based on taking the plastic through a very large structure and moving to some nearby point where the plastic are collected and cleaned. Thus, we can consider this problem as a multi-objective problem, optimal control problem. For this, we take a physics reference system with respect to the structure that carry the waste. And on the one hand, we put a Navier-Stokes equation, a stationary Navier-Stokes equation, with a force H, which is related to the gravity and other force as current or wind or other force. And on the other hand, we couple this equation with the equation of a transport equation, which is related with the density pollution. This is C. And here the control are F, which is the plastic elimination action, and also U gamma, which is the speed of the structure that carry the plastic. Therefore, we want to minimize at the same time the distance to a desired pollution in a certain sense, for example, in L2 norm, and the energy used for clean the ocean. So we have to solve a multi-objective optimal control problem. And now we introduce the multi-objective optimal control problem. Here, as his name suggests, we have many functional that we want to minimize at the same time. In our case, this optimization is also associated with the resolution of control problem, because the functional have some variables which are linked by optimal control problem. By having to minimize several functional at the same time, the minimum is not well defined, and therefore we must define or study an equilibria. Depending on how we define this equilibria, we'll be taking equilibria, Nash equilibria, Pareto equilibria, or another. In this work, we will focus on Nash equilibria. Also, the study for Pareto equilibria has been also done in a previous work. Specifically, we have taken the objective problem that is with two functional to be minimized. Since studying in this case can be extended without any problem to more functional. In this case, we can say that Nash equilibrium is a pair of control F1 and F2, such that each control minimizes each functional, fixing the other variables. Now here we can see an example of Nash equilibrium and Pareto equilibria. Here we have two functional, the functional blue and red functional. And for example, here the Pareto equilibria has the curve who link the minimal of functional blue and the minimal functional red. And here the Nash equilibria has a point. It's 1 point in this case. If we see the Pareto equilibria form a curve called the Pareto front, since these points are those for which the two functional ones cannot be minimized at the same time. On the other hand, Nash equilibria minimize each functional setting the other direction. That is, for example, here, if we fix the horizontal vertical line, this point minimize the functional red, And if we fix the horizontal line, this point minimize the blue functional. Therefore, let us go on detail the content of this presentation. Firstly, we can see the definition and use the control theory to see some results related to the existence and characterization. And also we can see the algorithms for approximate the Nash equilibrium. Okay. We start with the semi-linearity PDE, and now we have two control F1 and F2, and we have also a function, a semi-linear function phi, which is impose this condition because we want that for any control F1 and F2, we have to ensure the existence of solution U. So now we have two functional. Then the Nash equilibria, as we have said, there is the two control F1 and F2 that minimize each functional fixing the other variables. And here we choose this functional. The first term is related with the distance to an desired state in norm L2, and it is multiplied by a coefficient A. Also we add the norm of the control in L2 multiplied by a number mu. Here we have the region control, that's it's little omega E, A. And also we have a desired domain who is the region or where we want to the solution is near to a desired state. And now it is important to say that is A divided by mu is small. The problem is simple, but is this value increase, the difficulty of the problem increase also. So now we have the formal definition of Nash equilibrium, and is as what happened in the real case. Now we have that a Nash equilibrium verified the condition that the respective derivatives are vanished and in the equilibrium. Now this characterization is very important to see the following result, that the following definition, that it is Nash quasi-equilibrium. And we say that F1 and F2 is a Nash quasi-equilibrium if the respective partial derivative are vanished in the quasi-equilibrium in the point. Thus, continue with the comparison with the real world. We have that here, using the classical theory of control, we have that the Nash quasi-equilibrium also solve the optimality system with the adjoint state phi1 and phi2. And the following result show us that under some condition on phi, and if A divided by mu is small, then Nash equilibrium is equivalent to a Nash quasi-equilibrium. This, the first implication is very easy due to the Karas-Kantakers theorem, but the other implication needs a bit more work, since we must to prove that this new functional G are convex, and we don't add the proof because it's very technical, but if anyone who want to ask can be asked. So now, sorry. So now we have another result that is this. We have that if A divided by mu is small, then there exists a Nash equilibria, and if A divided by mu is very, very small, we have the uniqueness. So this proof is thanks to Schauder fixed point theorem, and is the best result that we have obtained for existence and uniqueness. And now we go on the tiles of some algorithm to calculate a Nash quasi-equilibrium. Let us remember that Nash quasi-equilibrium is the solution of the optimality system. So we have the semi-linear equation and the adjoint equation and the condition of optimality. Then the first algorithm that arises naturally is a fixed point type algorithm in which the new control is obtained from the previous adjoint state, that is here. And also we have another two algorithms, which are the optimal state gradient kind and optimal state conjugate gradient kind. Let's observe that they are gradient type or gradient conjugate gradient kind algorithms. In this case, we have two functional, not one. But in both cases, we have the direction of descent if it is marked by the partial derivative. So it is analogous to a gradient method or conjugate gradient. So now we pass to see the Nash equilibria for Navier-Stokes stationary Navier-Stokes system. Note that here there are some new difficulties because the first one is that now we have a system, we don't have an equation, and also the very important difficulty is that here is strongly non-linear, so we can use the same theory as before, because here we don't have a semi-linear case. Another important difficulty is that here in this world we don't want impose the uniqueness condition, so we consider the functional which depend on the control F or F1 and F2 and the solution U. So all of these difficult cause, for example, that the question such as the existence of Nash equilibrium are still open. On the other hand, thanks to the Dubovinsky-Mijutin formalins, we have been able to see that an equilibrium is a quasi-equilibrium of Nash, although we have not been able to prove the opposite implication, but this it is true. As we have said, we have not imposed condition of the uniqueness, but we know that if we impose a condition on mu and on the size of A divided by mu, we can prove the result analogous to the semi-linear case. Another important observation is that the result that an equilibrium is a Nash quasi-equilibrium is valid regardless the value of nu and in the value of A divided by mu. Recall that in this case, Nash quasi-equilibrium is a pair F1 and F2, so that solve the optimality system. Now we have the Navier-Stokes equation, and after the adjoint equation and the optimality condition. And for this case, we consider the functional before mentioned, and we will see how compute the control, the quasi-equilibrium Nash, the Nash quasi-equilibrium. So if we have here, okay. If we can consider algorithms analogous to the semilinear case, such as the fixed point algorithm, gradient and conjugate gradient kind algorithm. And in this case, also we have included a Newton type algorithm. That algorithm gives a very good result when it's come to simulation. And if we see this new algorithm, it is based on iterating the value of nu, and we have to find the solution of this equation of partial derivative equal to 0. And for each nu, we have to solve this equation, and after we iterate on the value of nu. Here we can see the initialization of the algorithms. Now we began by solving the Stokes equation, and after the adjoint equation. And here we choose the new control as the adjoint state, and we iterate the new value by as the maximum of new data and a factor for before the previous new. And here we can see the loop of this method. And for each nu n, we have to solve the equation for the partial derivative, and here the expression. And after we have to solve with a new nu and new data. Now we are going to detail some simulation that we have done for the Navier-Stokes equation. Now we have carried out 3 different tests. The first one is correspond to a domain composed by 2 rectangles. There is one larger that is connected by the smaller, and here there is a band, which is the control region, and here in the smaller also there is a band, which is the control region here. And we consider that the big rectangle is one desired domain, and the small rectangle is the other desired domain. The functional here considered are the before mentioned, in which one corresponds to the distance of the solution in norm L2 to a desired state, preceded by the coefficient A, and following by mu, and by the norm L2 of the control in their respective control underside domain. In all of these tests, we use a distributed control in such a way that this is equivalent to a border control in the part of domain that connect the control domain with the entire domain. And this is the desired solution, the desired state. We want that in the in the large rectangle, we want that the solution is rotated. And here in the smaller, we want that the solution is stationary. Here we can see that the problem of finding an equilibrium in the multi-objective optimization, because we look that for the solution, if we want that here the solution is rotate, here cannot the solution be stationary, and vice versa. So we can to find an equilibrium. No? So it is true that theoretically we don't know if it is possible to find an equilibrium, but in practice we try to find an quasi-equilibrium. It is the solution to this optimality system. So here we can see some results. So here we can see some results for different mu and a value, and for the coefficient, the number Reynolds. And we can see that here the solution is near to rotate, and here is close to be stationary. Oh, sorry. And this is the adjoint state for this case. Now we can see the second test. Here we try to simulate a bifurcation in a pipe. In this case, we assume that our control region are this rectangle and the other one. And we can assume that the fluid enter by the pipe, and here the fluid can be short or enter in the pipe, and in the lower also. And we have the desired domain here, and we want that the desired domain, the fluid sort with a Poiseuille profile, and here we want that the fluid don't sort. So we consider now all in a similar way of the previous test, the same functional, and we solve the problem for different number of Reynolds, and we see that if the fluid enter with a parabolic profile, the solution are this. And we can observe that if, here. And we can observe that the solution for different number of Reynolds numbers. So in the third test, we have a pipe again with two control rectangles. It's similar to previous test. But here we don't have a bifurcation. Here we want that in this rectangle and in this rectangle the solution behave in a certain way. Here we have, we want that in this rectangle the solution rotate, and here we want that the solution stay stationary. So we can see here the solution for, here there is another. Okay. Here we can see the solution for the coefficient, the number of Reynolds, and here we can see that A and mu is very large. If A divided by mu is very large, so the situation is more complex. And if we increase the Reynolds numbers, we have we can see that here can be appreciated some vortices. but this is the solution that is very near to the desired state. And finally, we can set some open question, and we want to comment that there are some results that it's not yet proved, as the existence of Nash equilibria, or the implication that Nash quasi-equilibrium is a Nash equilibria. And this result is very useful because we compute the Nash quasi-equilibria, so is theoretically is to prove that, to verify our algorithm. So we think that if mu is sufficiently large, and if A divided by mu is small, can be say anything, but it is equivalent to say that we want to impose the uniqueness of Navier-Stokes equation. Also, we have to, now we have working on extend this study to the case of evolution Navier-Stokes and to the Boussinesq system, which is the problem that will be connected to the plastic islands and to the other problem. And it is all, and thank you very much for your attention and your time.
Thank you, Irene. Maybe there's time for one question. The public, someone has a question, can unmute the microphone.
Víctor Hernández quiere preguntar algo.
Okay, Victor, you can use the microphone. Thank you. Okay, the microphone. He says that for the semilinear elliptic case, is it possible to relax the linear growth condition you have for the nonlinearity, and
yes,
so that they have a quasi-equilibrium or equilibrium? Is the question of Victor.
Here, sorry. Yes, for the semilinear elliptic equation, if we relax the condition, the problem is to ensure the existence of solution for any control F1 and F2. So we can think, for example, in the function superlinear, a superlinear function, but the problem is to ensure the existence of solution. That, for example, if the function is superlinear, the existence of solution is not ensured for any superlinear. We need also here, for example, here we need also some condition for the derivative, because we have to, if we study the Nash quasi-equilibria, we need a condition of phi and also of phi prime, because we need some estimate for the derivative, the first derivative.
Okay. Okay. Thank you very much. Another question. Victor says thank you. So, okay. If there is no another question, we thank you again, Irene. Thank you very much.
Thank
you also, Claudia. We finish now.
Okay, gracias. Gracias por la invitación.
Thank you very much.
Okay, so for all the public, you're welcome for the next session, 1 week. Marius Tusnak in September 20.